Thank you, Jens. Thanks for inviting me. Happy to be here. Was catching a few of the sessions earlier today that were very good. So for those of you who do not know me, I'm a C++ programmer since the mid-1990s. I've worked on a lot of different kinds of systems. I am the author of Boost Date Time. I got involved in Boost in the early 2000s. And was one of the original authors on the Chrono proposals for C++11, and been in and out working on the standardization committee. Right now, I spend my time on the library working group, which means that I read every single paper that comes to the library. And so part of what I do is I try to take notes and prepare so that when the standard is actually getting to be finished, I can make presentations to the community and we can see what's going to happen in C++, in future versions of C++. So that's what this presentation is. For those of you who don't, live and breathe by what the standard committee is doing on a daily basis, you'll know that C++, despite the pandemic, is going to ship on time. And that's just a fundamental part of how the C++ committee structures itself since C++11. We call it the train model. So basically, whatever is there on the train ready to go when it's time to ship the next version of the standard will go into the standard. Now, that doesn't mean that there's no thought or preparation put into what we want to have in a particular release. There is a plan. You can read the link there. So that's another thing you'll see throughout this presentation. I have links to the various papers if you want to dig in. But there's a plan and there's a focus. And my focus today is on the library. But one interesting feature of the C++23 plan is it didn't really have a big plan for language features. Which is not surprising given that C++20 was a very large set of language features, including concepts. And anyway, 23 was sort of destined to be more smaller in the first place. But as you'll see, the pandemic is definitely having an effect as well. On the library side, the big features that people were prioritizing are networking module support, concurrency support, and bug fixes. So bug fixes may surprise you, but let's see if I can use the slides properly. So the thing is, of course, with plans is that plans are plans, and then there's the reality of what happened. And of course, COVID is the big reality that has really changed things. The C++ committee has basically always depended on face-to-face meetings. That's been its real, the way that the committee has always worked. And so because of the pandemic, the last meeting was in Prague in February of 2020, which was basically where C++20 was finally shipped. And so the feature freeze for C++23 is only a few months away. It's in February of 2022, and the committee will not be meeting till at least June of 2022. So the bottom line is that the features for C++23 have been almost completely developed doing virtual work. And I think there's no question that that makes it very difficult in certain sorts of features that need a lot of back and forth understanding and working through corner cases and so forth. Those things are just much easier to do face to face, than they are on a Zoom meeting. In addition to that, there's the time zone effect. We have worldwide participation, and getting time zones, that everybody can work in and so forth is difficult at times. So what's basically happened is many of the subgroups, like the library evolution group, the library group, were meeting on a weekly sort of basis, typically for an hour and a half, and we're trying to work through and do features. So long story short, C++23 is going to be a smaller release. I don't think there's any question. It would be hard not to be a smaller release than C++20 because it was so large. And there's going to be a fair number of bug fixes. I'm going to talk about some of those today. And I think that's probably actually really a good thing. We needed to change some of the things that we did in C++20. So those priorities again, so two big library features, that were shipped in C++20 were format and ranges, and some pretty big changes have been made, and many of those changes have been backported actually into C++20. We'll talk about that at least at a very high level. I'm not going to go through all the details of it. The good news is if you hadn't started trying to use the experimental versions of things, you won't ever notice. You'll just get a better product. The changes wouldn't have been made if we didn't think that at the end it was going to be a superior product, and it was better to break things before we had 5 million users, actually, depending on these particular facilities. Support for modules. We are getting some support for that, and we'll see that. I'm going to talk about that today. Concurrency support with coroutines, things like standard generator, some of the sender-receiver stuff. Those are things that, there's still some work going on. We'll see what happens with them. I think for today's presentation, I'm going to be focused more on things that are more of a certainty to arrive, actually. In C++23. Those things are still in a lot of work. So ranges and format, in addition to the bug fixes, are getting a lot of additional things. And then there's just another whole category here, which was sort of mopping up a whole series of features that didn't make it into C++20 because we ran out of time. And a lot of those things are coming in C++23. Okay. So here's the outline of the talk, and I know Jens has given me a little bit more time than I had at CPPCon, but for a variety of reasons, I'm probably not going to go too much longer than I went at CPPCon, and I will give you links here to, let you guys go explore all these facilities. Many of these things have open source and so forth that you can go look at. And the other thing I'll mention at this point is I'm going to keep this talk updated, so you'll be able to go back, and as things change, as things get pulled out or things get altered in some way, I will keep the slides up to date so you can actually use it as a reference going forward in the future. So there's a long list of things here. Just even the categories themselves would make a big talk. And so kind of the way I'm going to structure this is I'm going to pick and choose a few things. I do have slides for some of the things I'm not talking about. Not for everything. I'll show you things I'm just not talking about at all. But I do have slides for a bunch of these things. And like I say, you can go investigate those things if you want. I'm not sure, Jens, if we can do the audience participation easily. But we'll see when we get down a little further in the presentation. So some things I'm definitely not going to cover today, and it's not because these things aren't important. It's just, there's a limit to how much you can do in a talk. And in addition to that, some of these things are still in flight. So you see all the things at the top here are still under consideration by the committee. And so it's unclear whether those things, some things are closer than other things. Like with freestanding and flat map and flat set, I haven't given you the references here, but there's several papers for those. The things at the bottom here, move only function, that's actually done. It's actually in the working draft, but I'm just not going to talk about it today. So as well as invocar. The extended floating point, I'll mention that just briefly because floating point numbers are important in a lot of domains. That's highly recognized by the committee. We understand that there's a large group of people, in machine learning, embedded in other spaces that want to be able to use different kinds of floating point types. And so this paper here, 1467, would open up the standard to allowing that capability. There's an additional set of papers. The C committee, the C standard committee, is looking at a series of now sort of small floating point types and other floating point types beyond what C currently offers. And we expect those will land in C23, which should come out about the same time as the next generation C++ standard. So I'm not quite sure what's going to happen with those. I think those might take 26 before those are officially recognized. But since part of the C standard, they would likely get in your C compilers sooner than later. Okay, so let me see. So Jens, I guess I cannot see the chat here. So, okay. I don't know if anyone can send me questions or not, but if you have questions, do what you can to send those. And I'll see if I get to see them. Okay, so let's talk about string processing. Why do I put string processing first? Well, I think the reason for me really is that every non-trivial program I've ever written, of course, involves some kind of string processing, whether it's secondary or primary to the function of the programs. So it's important for a very large number of programmers. And so some of these things are very simple. I'm going to talk through the first two. I'll just briefly mention that resize and overwrite is a performance optimization for cases where you're going to reuse a string and you need to be able to resize it and rewrite data in the buffer. It gives you direct access to the buffer. The string view constructor is a very simple thing that allows you to construct a string view from a range. So I won't talk any more about those in any detail. So let's talk about the very first thing, which is just being able to figure out if another string is in a string. It's the simplest possible thing you can imagine, and it's unfortunately been lacking. You've written the find commands and used iterators and so forth. You'll know that this is a very nice thing. We also, as a reminder, we got starts with and ends with in C++ 20. So this contains is really the bookend to those features to sort of allow you to do some very basic string things in a nice way. And of course, this is in string view as well. And you'll see this is already implemented in all the major compilers. So that's an easy one. This one is a little bit more, it takes a little bit more explanation, I guess. So this particular code, if I have a function do it like this, and I have some complex set of logic in here, and I end up in some place returning or constructing a string with a null putter, currently in C++ 20, you will get a runtime exception or a runtime error, which is an unfortunate fact because in this case, it's absolutely clear that the compiler can deduce the fact that you're constructing the string with a null pointer. So what's happened in C++ 23 indeed is we've made that constructor fail. And so you will now receive a compile time error instead of a runtime error if you attempt to construct a string with a null pointer. So again, these are small things. It's one less razor blade, as part of C++, something that you might run into. Okay, see how I'm doing. Okay. So let's talk about modules. Modules, of course, is a C++ 20 feature, which was great, but with C++ 20 modules, we didn't really get anything in the way of support for the standard library module being modular itself. And of course, C++ 20 modules changed the compilation model in a fundamental fashion from the way we've been doing it from the very beginning. If you think a little bit about what pound include and that model actually entails. What it means essentially is a cut and paste of every single include file into your translation unit as you compile it. So the inefficiencies of this are well understood and well known. You, in many complex projects, get literally hundreds of files that need to be accessed in a translation unit, which basically means reprocessing those files over and over and over again. And so that's one of the fundamental, the fundamental thing that modules is there to address. In addition, it has extra features for being able to support access control in a finer grained way than we could in the past. For example, excluding all macros, so that, with pound includes, you get macros whether you want them or not. With import, you will not get macros typically. Modules are supported by a non-binary or a binary form translation of the header. That's not fully standardized, as it were, but basically each compiler is going to have their own. They're all talking to each other now. They're talking about having a shared one. We'll see what happens with that. But header modules were sort of a special case, which allowed you to create a header from a header unit like IOStream to create a module. So that was one way, and this is one way actually you can do standard library modules today on some of the platforms, as you can use header modules, in which case you just turn an include into an import, and then you'll be using modules. The thing about the headers is that really the right model? And that's really the question that needed to be asked for standard library modules. And there's been a number of different proposals and discussions over the years trying to figure out what the right level of things is. And in particular, how do we want to name things? How do we want to divide things up? At one extreme, you can imagine that we would have one module for every single type, which sounds like a nightmare to me, because then I'd have to say pound import for every single thing that I wanted out of the standard library. Sorry, I keep saying pound import. There is no pound on import, as you'll see in a minute. We could have one for each type. At the other extreme, we could have import std, which would get you the entire standard library, no questions asked. And in between, there's things where we could have things like standard algorithm, standard container. But the question is, how do we make the right size for programmers? What's the right divisions there? So going along with that consideration of the granularity are things like, what is it that we want in terms of teachability, for example? Well, import std is super easy to understand. It's also super easy to move code to that because you only need one import in every single file, and you can get rid of your standard library includes. So that's really a nice feature of that. The thing about it is that C and C++ have been together for a long time, and non-trivial C++ programs also have macros in them, like assert in particular is one that's commonly used. It's also the case that there's a number of C functions that are in the global namespace that come from C++ headers. So what do we want to do about that global namespace? Ideally, modules would not modify that global namespace. They would, in fact, just stick to std, and the subname spaces of the standard is one of the considerations. So it might surprise you to learn that, in fact, the answer that the committee has decided on for C++ 23, at least there will still be some consideration of other options, but for C++ 23, you're going to get two modules, essentially, import std and import std.compat. And that second one is really there for things like fopen and some of the other global namespace things from C. If you want macros, you're going to have to pound include them. The good news is modules are completely compatible with inclusion as well, so you can still pound include. And so I think the goal basically is this is a straightforward way that we can move things forward and get modules being used in practice. It's also simple for programmers. It's also super simple to teach and understand. And to be honest with you, I really like the idea of not having to remember what thing is in algorithm versus ranges versus whatever. That old model actually doesn't really add any value to my life. It just makes me have to remember where certain things are. So, of course, the question you're asking yourself is, what does this do to compilation times if we import the entire standard library as one single module, every single function, every single type? What does it do? Well, so Bjarne Strustrup and Microsoft and some others got together and, in fact, did some testing of this. And essentially, you can afford it. So import std is, in this particular experiment, 10 times faster than a pound include of IOStream. So that's good news in that the standard library in full can be made available. There's some other numbers on these slides. I won't dwell on them. If you want to see more about the methodology and what they did to do these measurements, you can look at P2412. But their summary at the end of looking at this and doing some analysis of this is they're expecting, that a realistic real world kind of example would be somewhere in the range of 5 to 25 times faster for modules as opposed to pound include. So let's hope they're right, because that would be fantastic, and it would be a fantastic thing for C++ programmers. But it would mean less coffee breaks, so that might be a little bit of an issue. Okay, so this one, as I mentioned, this is a high on the priority list. The final wording approval and design approval is pending. And so basically, these two papers here talk about these things. And I expect fully that we will see this ship in C++ 23. Okay. So next, let me talk a little bit about input and output. And so, of course, in C++ 20, we got std format, which is a printf style way to format outbound text into a standard string. And one of the additions to this, there's some additions and changes to that I'll talk about, but then also, why not be able to just go directly to the console or directly to a file? So that's what std print will bring us. And then in addition to that, if you've worked at all with the format capability, you know that you have to do template specialization. Not everything that's a part of the standard library has a template specialization for format, so that leaves users having to do that for themselves or work around it in some other way. And then formatting for ranges. This could have gone in the ranges section, but I'm putting it in here because it goes with the rest of the I/O. This is something that's really interesting and really valuable. And then the last one here is actually, even though we're making a major initiative, at least on the output side here, to change the way we do output, we still have streams, and we're going to still have streams for a very long time. And span stream is actually in addition to that, and I probably will skip over that. The slides are there. The author of the paper is at the conference. I saw Peter Summerland earlier on one of the sessions, so you can chat with him and ask him about it as well. But it's valuable in certain particular cases. Okay, so I think I said all of that. So let's look at a format from C++ 20 example. This is a very simple example. I have two values, a string and an integer on the right-hand side here. They get passed into the format. The problem with this is that my format specifier here for the second parameter is a string and not an integer or a decimal value like it needs to be. And as a result, in C++20, as it was shipped, what would have happened is I would have gotten an invalid format specifier at runtime as a runtime error. And that's problematic, in particular, given in the modern world we live in, things like this, even in C, this kind of specifier mismatch can be detected and warned on at least by the compiler, if not giving you an error. And so we would really like this, since this is a static string, it's a constant static string at compile time. We would really like this to not compile and give you a warning, and indeed that's what it's going to do. This is one of those fixes that was a backport to C++20, so C++20 is going to work this way. If you are using the FMT library has already implemented this, and this is actually output from that library in terms of what it looked like before and what it looked like after. And so there's actually a couple of links here. You can go and play with that yourself with the different versions and see how things have changed. I'm omitting a whole series of other related issues with the format API that came up. When implementers really went to go implement it, there were some other issues that meant that it was going to expand the size of the compiled code in a way that vendors thought was unacceptable. So there are other changes that went in, and that's why it's a complete breaking change. All of those fixes are backported to C++20. So when you get official C++20 support from a compiler, they will have done all of these changes and you will see them. So the whole idea of it being a runtime error will not exist. You can still, by the way, do runtime formatted strings. You just have to use a different API for doing that. So if you're familiar with the format, you know that you could provide a runtime string, which would override a number of those things. I'll also give a shout out to Charles Bartow's talk from this year's CPPCon 2021. If you want to know all the inside gory details of what happened in format, you can go see his talk because he talks about exactly what happened. He's part of the Microsoft implementation team, and he talks about what they went through and some of the issues that happen as part of format. Okay, so let's talk about print. As I was mentioning, print is exactly the same as format, except for now we're not going to just restrict you to formatting to a string. So that first bit of code that's highlighted is C++20. But in C++23, there'll be a new header called print. And that will allow you to do the same thing directly to the console without anything in the way. It will also allow you to do the same thing into a file or into a file stream. So you have the ability, or actually any kind of IO stream, or sorry, output stream. So the new span stream would be able to support this as well. This will allow you to do that directly. Now, there's another thing I'm not going to talk a lot about here, but one of the new elements of this is there's some overloads that are part of the whole print and formatting regime here that give better support for Unicode. For those who work with Unicode, you know that it's troublesome area for C++ in many respects. That is also part of this improvement. You can go look at the papers and see more information about that. This is actually really cool. We are using this. in the stuff that we're working on, that my team is working on currently, and I find it to be really nice. So we're at a point with the print functionality where you do not need to use streams really for doing output. So you know, with maybe the exception, maybe you're going to use them for files or something like that, but largely you don't need to use the IOStream formatting facilities. You can use these facilities instead. So again, this stuff is available in the FMT library. There will, by the way, be a print line version, so you don't have to put the \n in if you want to get a line feed. The one caveat I'll mention about this is not implemented currently in FMT. So if you go looking for println, even though it's part of the standard proposal, it's not actually in the library itself. So again, with the Godbolt links, you can go play with these things after the session on your own and see what they can do. So I think I mentioned almost all of this. This is in some final design review. It has not cleared LEWG completely yet, but it has a time that's scheduled for it to be completed. It's had several rounds of review, so it's in very good shape, and I expect that it will get through to C++ 23. So, of course, also, if you're familiar with format, you're interested in the performance. This is one of the reasons this initiative is strongly supported. And if you look carefully at these numbers, what you'll see here, this is you know, the standard for print. The IOStream is approximately 3 times slower. What's interesting is it's pretty close, so it may just be within the noise of the performance measurement, but it's as fast as C's printf. It's actually faster in the measurement. And you could actually see where maybe C++ has an advantage here because it can do some things at compile time that maybe C cannot with the var arg signature on printf. But in any case, it's very fast, which is a perennial complaint with IOStreams. And so I think this gets you to a place where you know, you could do all of your output anyway in this fashion. So a couple links there for you to go later on. As I mentioned at the top of this section, specializations for other standard library types that don't have format specializations today. Some of them will get fixed, some of them will not get fixed. They're going to be continuing. The big ones that won't be fixed are complex and file system path, shared pointer, unique pointer. So those are going to slip into the next. Some other things though, like thread ID and some of the regex and error code are should be fixed. Okay. So let me briefly talk about range formatting. It would be wonderful, right, to be able to take a collection or another kind of range of some sort and just be able to directly put that into the terminal. I mean, this has been one of those things where, you know, programmers have had to write their way around this. C++ programmers have had to write their way around this for decades. So right now, if you look at the FMT library, it has facilities for formatting ranges. There is a proposal that will bring that to the standard. This is one I'm not 100% sure is going to make it given the time. There's some complexities to it when you consider recursive collections or, you know, multi-layer collections and so forth. But in large part, it basically looks like what you see on the screen here. Here's a vector of values. And in this case, basically, I have a format specification which says, give me 2 wide with a hex value, and then join them together with a colon. And basically, this is C++20 format. So I'm just basically generating that hex string and then I'm putting it out to the console with the print as a string. So that just prints out what you see here. Here's another one where I just take a collection of strings and you know, I get some output that makes complete and utter sense for that string. Now, of course, you can combine this with other range adapters and so forth. So, you know, take 2, take 5, filter, all kinds of other things that you can do that are very clever. On some of the ranges slides, I'll show you a couple of examples of that. So you can go to the Godbolt link. You can go take a look at this paper and see what it proposes. It does a lot more than what I showed here, including handling complicated things like tuple and pair and some other things. So a lot of really interesting work there that would make our life a lot easier for doing I/O going forward. All right, as I mentioned, I'm going to pretty much skip span stream. I will show you this one slide. But basically, span stream allows control over the buffer that goes into the stream. This was a feature that came from the original I/O stream in the 80s. Look up Peter. He'll love to tell you about it, I'm sure. There's iStream and OStream versions of it. And it allows you to get spans in and out as, for example, your primary utilization. You can also make your buffer be other things, you know, within the span stream itself. Okay, so that brings us to ranges. Now, this talk, you know, the entire talk could be about ranges. There's enough material here that we could talk about this all day, which is another reason why I'm going to jump over and do some highlights. There's multiple dimensions of new things here that change things. So the first thing is fixes to C++20. We'll talk about that in a minute. And as you know, ranges are divided into algorithms and then range adapters and views. So there's some of both of those also added in. And then one of the fundamental things that was missing is the ranges to capability. So take a range and make it into a container. Now, a range is a container in the first place, but the idea is that you can take a filtered or, you know, some kind of processed range and, you know, have an output container which you would then put the result into. This next one, pipe support. So if you've used range adapters with the pipe syntax, you know that's a very convenient syntax. It's very nice, elegant code. Unfortunately, with C++20, the way the standard is written, while you could create your own user view, you could not create one that has pipe support that interoperates with the standard library. So that's something that we definitely want to rectify, because there's no way the standard library will have all of the view support that you could ever imagine. And of course, we want users to be able to write their own, you know, so, and we want them to be able to interoperate with things. So I kind of think this is almost just a slight overlook from the C++20 ranges, and you can consider it a bug fix, but it opens up an important thing. It also means, again, we don't have to put every single conceivable view into C++ standard itself. And it, you know, it opens it up to Boost and other libraries to provide those things in a way that interoperates well. The next one, interoperation with non-range algorithms. We'll see about this one, whether it's going to happen or not. I'll briefly talk about it, but basically, this is the ability for non-range algorithms to play with ranges better. And then this all didn't, you know, just happen. Again, there was a sub-plan here that Barry Revson and Tim Song and some others, Connor Hoekstra, put together, you know, to try and move ranges forward. So They split the work up into tier 1, tier 2, tier 3 kind of work, and tried to lay out a plan for what was the most important set of facilities to bring in C++23. And a shout out to Tina's presentation from this morning, how to rangeify your code. If you did not see that presentation and you're just getting started with ranges, I highly recommend it. It was very good. So definitely take a look at that. Okay, so let's do the 1-minute review of ranges, because I'm going to show you a bunch of code on the next slide and slides, and just a little tiny bit of theory. But basically, right, a range is just something that can be iterated over. It has a begin and an end, and the return iterators, the classic collections and so forth we've had forever. Range algorithms, of course, then are algorithms that instead of taking iterators, they will take a range. Of course, all the ranges algorithms also take iterators, but predominantly we want to call the range versions of them when we can, because it's simpler and it's better. And then views are just another form of range, and they have this sort of lazy property. It's not given that all of them are that way, but for the most part, they don't calculate things when they get constructed, and they can be chained together with the adapters. That's the last piece of it. But they're cheap to copy. Some of the properties on views got changed as part of work for C++23. And they got back changed in C++20. So we used to think about views as never having ownership, but that really isn't true, because there are some exceptions to that rule. For the most part, it's true, but there are important exceptions where we now actually have an owned view in the standard, because when something, when a view has to own something, say a shared pointer to something underlying, there are cases that we want to be still able to use views, but so we have to relax some of the constraints that were originally there for C++20. Okay, so the simplest ranges code in the world is, here's an array of values, and I used to call it this way with begin and end and 2 iterators, and now I just call it, with ranges sort. And that's it. So, that's, for me, again, the 90% use case for developers is, instead of calling a traditional algorithm that requires you to pass in the begin end, find a ranges variation of it if it exists, and make a call to that. It will do what you want, and it will be cleaner and simpler. Okay, so we got a whole host of new algorithms. And some of these you might recognize, some of them you may not. Shift left and shift right were actually new regular algorithms in C++20. Unfortunately, the range versions of those algorithms did not make it into C++20. I'm not going to talk more in detail about those algorithms, but again, there are slides, you can take a look at them. Fold left and fold right, I'll talk in more detail about. I'll briefly cover starts with and ends with. You can pretty much guess what those are going to be about. IOTA as an algorithm and not as a view. So in C++20, we have IOTA view, but now in C++23, we're also going to have IOTA as an algorithm. That was missing from the rangified algorithms. And then find last is kind of on the bubble. I hope we're but find last is basically a way to quickly look backward through a range. If you've ever tried to write code with reverse iterator and so forth, it's actually surprisingly difficult to get this code correct. And so this is a nice utility. And this would be both in ranges form and in non-ranges form as well. Oops. All right, so fold. Fold is a generalization of the accumulate algorithm. And if you have worked with the ranges algorithms in C++20, you know that accumulate was not one of the algorithms. And that was in part because none of the numeric type algorithms actually came about in C++20. So fold is the first of a few algorithms that I expect to see. And this one should be in C++20. So it's a generalization of accumulate. Just like other C++20 range algorithms, it has projections. So if you've worked with projections, that's a way to filter the range as the algorithm processes it. It takes two forms. There's the directional part of it, which is either go from left to right or go from right to left. So in other words, forward to back or back to forward. And then there's the question of how do we specify the initial value? With accumulate, you have to always specify an initial value. Fold, on the other hand, allows you to either specify an initial value for the actual calculation, or it allows you to use the first element of the range instead as that initial value. So that's what this first and underscore last variant of it is. Those underscore first and last mean underscore first, use the first value of the range as the initial value. Or when you're folding from the right, you'd use the last value of the range as the initial value. So here's a simple example. The signature, simplified, of course, looks something like this. We get a range, we get an initial value, and there's the projection, which is defaulted to do nothing. So a very simple example is, add the sequence of things in this vector together. So it's just like you would expect from accumulate, and you'll get a numeric result here. Okay, so I think that's going to be kind of it on algorithms. Oh yeah, I said I'd mention starts with and ends with. So starts with and ends with does exactly what you think. It's a predicate. It's going to evaluate a range. In this case, I'm actually using an IOTA view, which is interesting. It's going to evaluate that, this first range, 0 to 10, starts with the second range, 0 to 5. And yes, then you'll do something and so forth. And ends with the same kind of concept. And so you can do this very straightforwardly. All right. So views and adapters, and here's where we can see a lot of major additions to the library. So we have adjacent, which was missing in adjacent transform, which actually goes along with zip and zip transform. So that's the ability to look at multiple elements in a sequence as you process through. Cartesian product, which I think we're going to skip over that one, but you can look at the slides. But that one's going to give you basically an unrolled for loop or a series of for loops, depending on how many different ranges you're putting together. Chunk and chunk by allow you to group parts of a range together, and slide allows you to see a part of a range for a time and move that view along a particular range. And then join with, you might be thinking, well, we already have join, which we did get in C++20, but join with allows you to take an additional delimiter and join a range together with that delimiter. So I'm not going to go over that one in more detail. You can look at it elsewhere. So let's just go back again and look at some C++20 code here. So this is, again, ranges 101 code. I have a standard vector event. I have a predicate here, which just tells me whether or not a particular integer is an even value. And then I'm using those properties I was mentioning previously about copy to cheap to copy and the laziness of a particular, particular view to basically create, a view here on the stack. So this thing evens is the actual view. It is made up of looking at the vector and then filtering it on even values. But no calculation is really done at this time of construction. That's really just the construction of the references and so forth to the underlying things. To actually do something with the view, I have to actually iterate over it intentionally. So I have a range for loop here where I just go through and print everything. I can do the exact same thing different ways. This is a filter view version. So instead of using the adapter here, I'm just using the filter view. And in this case, I'm passing the vector and I'm passing the predicate to the constructor. These things are exactly equivalent in terms of the underlying facility of how it works. They're essentially synonyms for each other. I think these days, most people are preferring this adapter style where you construct this. Now, by the way, I could have constructed that right in line in this for loop as well. In this particular case, I just did it as a demonstration that you can, capture it on the stack and then use it later. Okay, so that's all just C++20. And so, as I mentioned, mistakes were made in C++20. And so actually we had breakage in a bunch of different places. Nikolai Josudis brought to our attention inconsistencies in the way iStreamView worked. That was broken. That should be fixed. Join view had some other issues. Split view was far less than optimal the way it worked. So that actually got renamed to lazy split view, and a superior version, in particular for string processing, is now called split view. So this stuff was all backported. It is all being backported to C++20. So if you haven't started using C++20, you can ignore it. It'll just work the right way from the beginning, and you won't have known that it was not in an optimal form prior to fairly recently. So, okay. So here's an example of that other case I mentioned at the top, non-range algorithms in ranges. This is, I've got, my standard vector event here, and I'm using an adapter to do a transform. And so I'm transforming each one of these elements by squaring them, basically calculating the square here. But what if I wanted to actually, sum that all up? Well, and I wanted it to be parallel. Well, the range algorithms are not parallelized at the moment, so you have to use the standard algorithms. So it turns out in some implementations, this probably does not work currently, which is unfortunate, right? Because there should really be no reason why this particular range is special, but it has to do with the requirements on the iterators for these algorithms. We will see if this gets in. I do not know. I honestly do not know. This has not been implemented anywhere, and that is usually a big problem. And so we'll have to see whether or not people can get this implemented in time. Tested, make sure it doesn't break anything else, because that's important. I think it's a really nice feature in the sense that it, you'd expect to be able to do this. Honestly, I was surprised when it, didn't work. I didn't come up with this, but I was surprised when somebody showed that it didn't work. And so it would be better if it works, because it really should. Okay. So the pipe support for views, let's just talk a little tiny bit about some of the theory here. So if you think about what ranges do, and if you think about my slide 2 slides ago, I kind of showed you this thing of adapters and views. They're very similar to each other. And in fact, the adapter generates a view And it does that in part by allowing you to have this pipe syntax. And this pipe syntax essentially gets turned into a view constructor, that looks like this. So if this is this is called a range constructor closure object, and that's really the meat of what's going on in this proposal. And so to be able to do this, you need to have a way to access the range adapter closure object, and this facility will name that properly and will allow you to do that. So then you can make all of this logic work exactly the same. If you want to see the gory details of this, Jason Rice did a presentation in CPPCon 2021. There's a link to the paper. I think the CPPCon stuff obviously isn't fully published yet, so there's no links at this point. But anyway, if you really want to know all the gory details on what that's all about, you can go there. All right, and I'm going to skip Cartesian product. I'll just show a couple of quick slides on things like chunk. So here, I just want to divide this range up into groups of 2, well, except for I have an uneven number. So chunk is the case where it will give you as many as it's got. And so this is chunking it up. And by the way, this is printing a range. So you see here that same pipe syntax of the vector into the view adapter, and so you can just write this code directly. You don't need to put it on the stack. You don't need to construct it intentionally. So this is another one of those things where it very much minimizes the amount of code. And again, this code working is dependent on that range printing capability being finished. Slide is a similar kind of situation, and it just slides over the view. Chunk by gives you a predicate, so you don't chunk by fixed size, you chunk by evaluating to see whether or not a condition has been met. Let's talk just briefly about zip and zip transform. That's a really important capability if you want to put multiple collections together, especially if you're dealing with things like tuple and pair. There's actually a huge number of changes to tuple and pair to actually support this properly. And again, what you're seeing here now is this ranges print facility in with a zip. So basically we have several vectors. This one's numeric, this one is characters, this one again is numeric. So if I put 1 and 2 together, under the hood, I'm essentially creating a tuple of these things, which is then being printed out as part of this print statement. So you can see that this code is extremely powerful. This is code that we just simply cannot write in C++ 20. The economy of it for what it does and the fact that it's all very quick is just a very good thing. So there's some more here on the slides. There's some different ways you can do transformation. Of course, that's what the transform piece of things is. Okay, and I'm going to skip up to ranges 2. Which, as mentioned, is just a way to now take that range, like a view, for example, and actually make it into a concrete collection. Sort of the various simplest form of this kind of thing would be I've got some kind of a vector, then I do some kind of range-based transformation, and the last step here is this ranges2 call with a vector. Notice I didn't have to tell it that it needed to be a vector event. It figured all that out on its own. So it's pretty smart about that. And then again, I can just print it out and so forth. And you can go see this code work on Godbolt. It uses ranges v3 because ranges v3 has ranges 2 in a form that's similar to what's in the standard. What is going to come in the standard is more capable of what more capable than what's actually in ranges v3 currently. This is another example. I won't go through it, but it's a similar kind of thing with strings and manipulating it. So there's a bunch of ranges resources here. I apologize for this table in advance. There's a bunch of missing things here. It's part of the reason why I'm going to keep it up to date. There's more papers for me to put here that haven't gotten here yet. Okay. So I'm doing okay on time, but I'm probably going to wrap up in the next 15 minutes or so here. I don't know if I can do any questions. I'm still not seeing a way to do that in the interface, but maybe we'll figure that out. Oh, there is a private chat here. Let's see. Okay. Jens says he'll post questions here when we get there. Great. So constexpr, all the things, I'm not going to dwell on this. And I mean, everybody probably knows that many things are being, made more, as much constexpr as possible, just to enable more compile time programming. So variant and optional are two big things that got a lot of additional constexprs added to them. So I honestly, I've forgotten now if every last function is, or there are still a few missing ones. Unique pointer is one that might surprise you, since that's about memory management, but the constraints on constexpr and memory allocation have changed in C++20 actually, so that enables this to be possible. CMath is another interesting area. If you ever wanted to do any compile time calculations for mathematical things, you're using the CMath library. Not everything is there because certain kinds of things, and it was a big sticking point what to do about errors in compile time context. But essentially, it's going to follow IEEE rules, and if it would give you an error at compile time, then it's not allowed. So you can go read the paper. I believe I have links to that one. If I don't have links to that one, I should get them shortly. But you can also go find it. Anyway, those are some useful ones. And to chars and from chars for integer overloads, not for floating point, only for integer. And again, the floating point at compile time is a bit of a sticking point to understand exactly how it works. But we did get over that, I think, at least for some of the core CMath things. Okay. The containers, I'm skipping, and now we have utilities. And I don't know what the best thing is. We got a question about Hive or Colony. And the answer with Hive Colony is that is going to get deferred to C++26. Does ranges 2 allow you to provide an allocator that should be used for the container to be constructed by? That is a very good question. I believe it does. Yes, it does. It does. I do remember seeing that in the paper. So yes. Okay. Do we have any more questions? And I guess I'll also take, shout out for particular items that people want to see with respect to this. Monadic optional was actually covered by Phil in his talk earlier this morning. So you could actually go see that talk and see a little bit about monadic optional. And that's actually pretty simple. It's just 3 functions. Expected, I'll go ahead and go through that because I think that's of some pretty big interest. And maybe I'll go through stacktrace real quick too. So let's do those 2. So question is, any changes to the standard where exceptions are thrown in the past and where now terminate is called? Not that I'm aware of. There is a proposal that I'm not talking about, but we'll probably make it in. That's basically allows you to call a function called unreachable. And that is to indicate to the compiler that this is a branch of the program that should never be reached. But that's not quite what the question is here. So I'm not aware of this. The only ones I'm aware of are the two that I showed, which instead of an exception at runtime now turn into a compile time error, which is infinitely preferable. All right, so skip over Monadic. So let's talk a little bit about expected. Phil did also mention this in his talk earlier this morning. So expected is in some ways a fancy kind of variant that allows you to express a return value and an error return. And so like optional as well, it's very similar to optional in that it has very much the same interface in terms of being able to ask if it has a value or there was an error. But the error type is customizable. So you can make it a string, you can make it whatever type you would like, including void. The void case is one case here where expected does something that's different than optional. So if your return from your function would have normally been void, but you still want to process errors, you can use expected of void with an error return type, and it will all just work, which is something you can't really do with optional. So here's an example. I have some boost date time code here. Boost date time uses exceptions in its interface. So if you attempt to construct a time with a bad value, it's going to throw an exception. And so instead of that, if let's say I wanted to go from an ISO string to an actual time value, instead of exceptions, I wanted to make that an error return, I could do something like this. So in this case, I'm just try catching and I'm making unexpected. So this is the case where it's unexpected. And you see here the type that I'm using for my error is just std string. So I'm just catching the exception. I'm converting it into an error return. And this time expected return then will either have a p-time value or it will have an error string in it. So here's some code that uses it and exercises the good and the bad cases. And as you can see, no longer am I exception handling here. I'm evaluating a Boolean to tell that this value is no longer good. And I'm not really very happy with this particular error that comes out. That is the error that comes out, unfortunately. So this one is in the final phase of the committee, and it's been a long slog. It's actually a very big facility to specify, surprisingly, for something that seems simple on its surface. But it's in the last phases, and I expect that it's going to be done pretty shortly. Okay. And then also for error handling, stacktrace. If you've used Boost stacktrace, you would be somewhat, well, maybe I'll go back for a second because we got a question. Why would you return expected instead of error? I'm not sure I understand that question. So yeah, I'm not sure I understand the question, but in this case, basically, yeah, again, it allows you to have a type where instead of getting the exception, you can do that. From your point of view, how early or late should the trainer show newer features like ranges and format, comparing to previous alternatives to achieve the same behavior in common use cases? Well, to be honest with you, I think I would not. This is kind of like the old question, should we teach C first? And my answer is no, we shouldn't. We should teach more modern versions of things first, in part because they have superior properties. Those kind of facilities are better, they're safer, and they're less error prone than the former ones, especially when you get into views. If you watch my CPP-Con talk from 2018, I talked about how, ranges with views versus, range algorithms versus views. And I think even others have made this point as well in some other presentations I've seen, that the number of cases of error cases, like off by one error cases, for example, that you can get with a view, well, you can't get an off by one error case with a view, because when you use a range for loop to iterate over it, there's no off by ones. Whereas with a traditional for loop and a traditional set of algorithms, you would get that. So I think modern C++ first and legacy C++ later. Okay, so I think the clarification of the other one is, why would you use a void of expected versus an error type? I think maybe I said something almost wrong there. You always need an error type here. So you can't have a void error type here. But you can have a void for the return value of your function. So if you imagine that your function just does something and it doesn't have any kind of reasonable return, that's when you would make this first parameter a void. So hopefully that clarifies that question. And Julio converted the brackets. I don't know about that. I skipped over a slide with span as a function argument in it. Is that about fixing std span, vector, etc., and not compiling because of restrictions on a range constructor of span? Have those restrictions been lifted? I don't think anything has changed with span. My particular span slide was related to span stream stuff. So the answer is no, I don't believe this problem has been fixed. It's possible I'm wrong about that and something happened that I missed, because there's a lot of stuff. It's interesting. I can go check on it, but I don't think so. Okay. See if we got any more questions. All right, I think we're good on questions. So we'll do stack trace quickly, and then we'll probably close it up. I have about 20 more minutes before I have to go. So stack trace, if you've used Boost stack trace, you'll be familiar with this capability. This has been one of those, again, things that, especially in debugging contexts, has been really a challenge to do portably. You can imagine doing this even in production code, though, with certain exceptional conditions where you want to get detailed information about what's going on. So this is one of those items that was unfinished business from C++ 20. It was proposed. This has already been added into the working paper. As I say, it's based on Boost stack trace. There's a ton of details that are complicated here. There's going to be dependencies on compiler modes. If you've compiled your code and stripped your code of all symbols and so forth, you're not going to get symbols out of a stack trace. You're going to get some information that probably isn't too valuable to you. There's no universal portability with respect to what exactly comes out of the interface. What is portable is the interface is portable, so that in a portable way you can include the header stack trace. You can snap a stack trace in a particular place in your program, and then you can output it to IO streams, or you can output it to a string or an IO stream and process it somehow later, so you can log it, do all of those kinds of things. So, you know, and again, the details of what's in the stack trace are going to be a little different. You know, this is an example using Boost stack trace that was put together. And so the synopsis of what this thing looks like, you know, stack trace is basically a collection of stack trace entries with a description, a source file, and a source line associated with it. And, you know, you've got an operator for IO streams here as well. All right. So I'm skipping interfacing with C and calling the add exit function. So form and function are one. I think, you know, obviously this is C++ and C++ libraries have been getting more advanced, more capable, and still being fast and still being able to do things very close to the metal. And so we've opened up whole new dimensions of design capabilities with the features in C++ 20, especially 23, not so much, but I think we're getting a lot of nice new facilities that augment our STL2, so that's our new ranges library. This is the link that I'm going to keep up to date. I'm sorry, it's CPPCon, but I only want to keep one of these up to date, so that's the one to go to. And I don't know if I can, since I can't access the chat directly, maybe I can put them in the chat and Jens can put them in. So these other two links, if you have not been to you know, CPP reference for compiler support, if you want to track closely what's going on, right? This is now really the go-to place to track what's going on with features. The only one disadvantage of what happens in CPP reference here is that the only things that get listed here for C++ 23 or any other feature are things that have actually been voted into the full committee. So I showed you a whole bunch of things today that haven't been voted in by the full committee yet, but I'm expecting that they will be, assuming that all goes well. So here's actually the list of C++ 23 compiler features. So there are a few language features, and you can go take a look at those. And then you can see here the actual set of library features that have made it all the way through the process. And if you look at this list carefully, you'll see there's probably a few things that I, again, did not even talk about leaving out. But when C++ 23 is complete in February, when you come back to this site in February, you should be able to see the complete content of C++ 23. So that's why I linked to this, because it's the go-to place for finding that. And of course, if you want to know what add exit is and you don't know, of course, go there. And with that, I think I'll say thank you. And I certainly am open to taking questions for another 10 minutes or so here.
Okay. Hello, Jeff. Thank you for your talk. Let's see if there are any questions to be taken from the chat. Let's give them a minute to catch up with the stream. And there I am. So one question I would have is, like, how complete is the library for C++ 23? Is there like still a window for a lot to go in, or is this like complete?
Yeah, it's the completeness is that the library evolution has looked at its backlog and has set up a series of meetings between now and January, which is basically the point at which they have to stop work on design features and pass all of it to LWG for final wording. And so there is no room in that schedule for anything more. So if it is not in a paper already, then it will not be in C++ 23. It is also the case that, like, you know, Hive as an example, it was something that has been, was something that's been in the process and been worked on, and LEWG has looked at it. But the judgment call was that it probably wasn't going to make it, given that it's, in a medium to low priority. So they just took it off the table for C++23 for the moment, just because of the lack of time to actually process it fully and be sure and confident that it's a good facility in all respects. Okay, so question, does stacktrace make specific requirements on reporting stacks containing inline functions? And I think that's another one of those examples where your mileage is going to vary. I don't expect I don't expect it to be the case that just because you put a stacktrace in an inline function, that it's going to be a problem. You should be able to do that. Whether or not you'll be able to see the symbols for it, we'll have to see what the compiler vendors actually do. If you look very carefully at that thing I flashed on the screen, nobody's actually implemented it yet. None of the vendors have implemented it yet. And actually, if you look at, if I go back to this just for 1 second, as I mentioned, you'll see with a lot of these other things, like the string contains, some of these other smaller features, many of the compilers have already implemented these C++23 library features. So you can get them if you've got the most advanced version of the compiler and you use, 2A usually is the flag, or depending, I think it's latest on Microsoft's compiler. So any known ABI breaks in C++23 STL? Well, the known ABI breaks in C++23 STL would be in ranges, which is STL 2.0, as it were. And so it's not just an ABI break, it's an API break. In other words, it's not just that the binary is broken, but the actual, what you're going to get from the function called, split view is not the same as it was when we shipped 23. So yes, those are the only breaks, though. Format is the other thing. There's none in the standard, I dare to call them legacy algorithms, the old school algorithms that are just in STD. There are no breaks there. There are really no updates there either, except for if find last gets in, find last will have a regular algorithm as well. All right, so I will try and consume that tab so I still have it.
Yes, so I think that brings us to the end of your talk.
Okay.
Thank you so much for coming. It
was an awesome talk. And thank you for inviting me, and I hope we can do this in Berlin next year. So.
Submit a talk. Yes, of course. And okay. Yeah. So.
All right.